Now I would like to give the floor to you, Clare, and let's hear about setting standards for extensively hydrolyzed formulas. So now we go to the more younger consumers with food allergies.
Thank you very much, Sabina. Okay, so setting standards for extensively hydrolyzed formulas, and this is my declaration of interest. I do have a project from Nestle which is actually for analytical work, and I have shares in Reactor Healthcare which produces food challenge materials. So if we're going to think about standards for extensively hydrolyzed or other types of hydrolyzed formula, one of the things that I think is really important is to understand what the relevant cow's milk allergens are that we need to be considering. And obviously we've got, it's very interesting, I've been part of a European Food Safety Authority project looking into clinically relevant allergens. It's actually quite interesting looking at the data on cow's milk allergens because molecular allergology has moved on since the beginning of looking at this, and actually the evidence that we have on cow's milk allergens is actually not as good quality as some of our tree nut allergens. But nevertheless, we have the data on molecular allergology of cow's milk allergy in this wonderful review that Carmen Regioni did with others in EAACI, which is showing that caseins give you 93% specificity and sensitivity and specificity using a cutoff value. And it's interesting for me to see how the molecular allergology really works better for those when they set particular cutoffs, which aren't necessarily the same as the positive test results which Fadia for Thermo Fisher actually provide. They're much higher levels of IgE. Similarly for alpha-lactalbumin and for beta-lactoglobulin. So those are our clinically important molecules that we're thinking about in cow's milk allergy. There are other allergens that have been identified, serum albumin, IgE, lactoferrin, but those are the ones that I'm going to focus on because clinically they seem to be the most relevant ones. So let's think a bit more about those molecules because some of them are really interesting, and caseins are incredible molecules. They're an important component of milk, and they have actually a very, very flexible structure. So we don't have those nice, neat molecular structures, although these days if you go into UniProt, AlphaFold will try and spit something out to you, but actually they are termed rheomorphic, and that is because they're really mobile, they're moving around. And they have a really, really important function in milk. And it's actually, I think it's amazing myself. I don't know whether this laser point, yeah, there we go. So what they have are phosphate groups on them, and they will bind calcium above its solubility level in milk. And that is a really important part of casein's function in milk, is to bind that calcium and make it bioavailable. This structure of casein and the casein micelle comes from amazing work done over many years by a guy called Carl Holt. It's still a matter of debate in the food colloids community, but we think now that calcium phosphate forms nanoparticle structures of 6 nanometers, 7 nanometers in size, and those become assembled into this casein micelle, which is coated by kappa casein. So in here we have our alpha S1, alpha S2 and beta caseins that combine the calcium. They're then packed into this large micellar structure, and that is 100 to 200 nanometers in size, and that is the reason why milk appears white, because these molecules scatter light. So this is an incredible structure, but it tells you about the protein and what it does and important interactions that it has. So then we come on to our whey protein allergens, which are the other two important ones, and here we have the molecule beta-lactoglobulin, which is quite fascinating because you find it in ruminant milks, but not necessarily in human. And it comprises 2% of milk protein. And I still think, having worked in this area for a long, long time, we still don't really know why beta-lactoglobulin is there and what it's actually doing. It's an amazing protein. Structurally, it's really tough, it's very stable, and it has a pocket. And what you can see here is where a molecule will bind. It binds retinoic acid. We don't know whether that, still don't really know whether that is its biological function, but it can bind a lot of different lipid molecules. The other whey protein is alpha-lactalbumin. Now, this is a different guy, really, really important in the biology of milk and how it is made. And that is also a very important calcium binding protein. It is much less stable than beta-lactoglobulin, but it has the capacity to interact with lipids and lipid micellar structures. And actually, sometimes it can be protected, bits of it can be protected from digestion by sticking on lipid molecules. So those are our proteins. So they have different structures, they have different properties. All those epitopes that they contain, so just to think about them in terms of their IgE binding capacity, is we have epitopes, and they can be modified. The processing can modify the ability of foods to cause allergic reactions by disrupting those epitopes. So we have two different types. This is all work that was done actually many, many years ago by a guy called Mark van Regenmortel, who was instrumental in defining conformational and linear epitopes. So if we think about conformational epitopes, that was different parts of the protein structure are brought together and your IgE recognizes it. Now, those types of epitopes can be really modified by heat and disrupted. But we then have these other, what we call linear or continuous epitopes, where a long stretch of amino acid structure binds IgE. Now, what's interesting in milk is obviously our whey proteins are quite globular, and they have many conformational epitopes, so maybe thermal processing can get rid of those. But caseins are a different ballgame, and actually they are full of linear epitopes that are probably really very stable to any kind of thermal treatment. So, sorts of treatment that are used in food, we have extremes of pH. Lactic fermentation causes proteins, milk proteins, to coagulate, the casein micelles. We have other things like heating, blanching, and any kind of powder that you buy, whether it's skim milk powder or your infant formula, it is likely to have been what we call spray dried onto drums at very, very high temperatures quickly, but you have it heated in all sorts of different ways. And then lastly, we have hydrolysis. Now, the food industry uses acid hydrolysis. You get hydrolysis happening as a consequence of fermentation, but particularly what has been used in the last 30 years is industrial enzymes to digest proteins. So we have ways in which those epitopes can be removed, or particularly for the conformational ones, they can be disrupted by all those sorts of processes. But you can also hydrolyze your peptides. Now, if you're talking about linear epitopes, the way you're going to get rid of those is by hydrolysis or chemically modifying them so that the Ig epitopes are removed. So that's what gave rise, I think, to many of the ideas or understanding of how hydrolysis could be used to actually remove or reduce the allergenicity of foods. This is a process workflow actually for producing bioactive peptides from milk, but it shows you the principles of how this might be achieved in a manufacturing environment. And you have, I think you can see it's really quite complicated. There's lots of filtering steps, but you have the ability here, you use enzymes to actually cause this hydrolysis, and then you use all sorts of filtration to remove those enzymes and ultimately give you your hydrolysate. So those same sorts of approaches are used to make hydrolysates that are used in infant formula manufacture, and we have two different types of classification. And what's interesting in putting this talk together, I was going back through the literature to try and find where did these definitions come from. The one that I could find was from Pediatrics back in 2008. So that's what's here in the slides. And there they had a definition that a partially hydrolyzed formula or protein comprised peptides less than 5 kilodaltons in size, and that for an extensively hydrolyzed one, it was less than 3 kilodaltons. And any protein chemist will say the difference between 5 kilodaltons and 3 kilodaltons isn't an awful lot, but that's what was in the definition. And often what happens these days is you've got that partially hydrolyzed protein that's been produced with the enzymes, with hydrolysis. The extensively hydrolyzed ones use much harsher conditions, more hydrolysis. But importantly, what we've realized is putting them through a 5 kilodalton filter actually can get rid of any residual big proteins, and that includes potentially the enzymes that have been used in the manufacturing. And I think that's where we have advances in technology that have happened over the last, 2008, at least 20 years, that have actually changed manufacturing. So let's see what we know about that impact of hydrolysis on IgE epitopes. So if we think about partial hydrolysis, and this is some work that was actually done by the team in EAACI with Hervé Bernard, and actually using the enzyme plasmin, they were trying to actually identify IgE epitopes, but they showed if you have partial hydrolysis, that actually you still keep your IgE binding epitopes, and actually quite big fragments have those multiple IgE epitopes. And then if you look at another study where you can actually see different types of hydrolysis, and this is the hydrolysis on this side of the slide, quite difficult for me to actually see this. Sorry. And you can see here what happens with the increasing degrees of hydrolysis. You see a decrease in IgE binding. So we know that that hydrolysis is actually reducing the size of the peptide fragments left so that they cannot bind IgE. And if you think about the capacity to bind IgE, which is measured here, is in an ELISA. So actually you could have something that had 15 amino acids. I think we think that's probably the limit of the size of an epitope, the smallest you can get that binds an IgE. But on its own, that will not cause an effector cell to release histamine, because obviously there you need to have multiple epitopes. So it may well be that you need much bigger fragments, like the 5 kilodaltons, that actually are important, could still be there binding IgE. So this is some really nice work done by Katrina Bow, and I hope I don't distort it too much as she's sitting in the audience listening to me. But this is a really nice study, and I love it because it combines physico-biochemistry with measures of immunogenicity. And what Katrina and her team did in DTU was actually look at a beta-lactoglobulin hydrolysate and a whey hydrolysate. And they characterized not just the peptide size distribution using mass spectrometry and showing, these are mainly peptides that are really very small. Most of them are well below that 2 kilodalton range, 3 kilodaltons. But when they did gel filtration chromatography, what you can see here is that there's probably an indication that actually there are peptide aggregates there. So these peptides, and especially, this is a whey protein one, but casein peptides stick together. They do all sorts of things because that's what they're designed in biology to do. The question then is, well, okay, I've got it made really small. I have some aggregates there. What happens to the immunogenicity? And Katrina does a lot of work with a brown Norway rat model of allergenicity that was developed in DTU. And what she showed here was that actually these peptides are there, but they are not immunogenic. So actually that shows if you've got a really good hydrolysis process, you can reduce both the IgE binding, but actually you reduce the ability of those peptides to sensitize. And I think this is a really nice study showing that. So then what happens in real life? So this is a study that was actually done by Rosendahl and Vibeke Barchold, who was also in DTU many years ago. And we're talking 1999. Things have changed a lot since then. So this is where we were then. And this was a SDS page analysis of all different types of both partially hydrolyzed and extensively hydrolyzed infant formula that were available at that time. So one of the things that first you can see on this SDS page gel is some of these things have quite a lot of big stuff in it. and some of them don't, even though ostensibly they're calling themselves the same thing. But actually, a lot of this, the extensively ones do seem to be much more hydrolyzed than the partially hydrolyzed ones. But there are still issues potentially of residual large amounts of material and a lot of heterogeneity in what was called the same thing. As you come on, next one. So one of the other issues at that time was that those residual large fragments that were found in some of the infant formulas meant that there were recommendations and concerns over adverse reactions to those formulas. And I think that was one of the things they were saying. This is the recommendations from a paper from that time, 2002, about how those formulas should be used and the concerns there were over highly sensitized infants reacting to them. But of course, things have moved on since then, and there really have been a lot of advances in the manufacturing processes and some of the tools that we have available to us for actually monitoring quality. So hopefully things have improved. So this is some work that actually Sophie Newton from Nestlé did with others, actually just to look at what the variability was. So up here, we have that peptide size distribution. So it's like the same sort of work that was done by Katrina and DTU. And actually what you can see here is there's a lot of these have very, very small peptides left in them. But there are others up here that are very high. So we still have that problem that some things may be called the same, but actually have very different peptide profiles. And if you look at this analysis of, for example, beta-lactoglobulin left in these formulas, actually a lot of the higher levels of intact BLG were found, and these were in samples where there were bigger peptides found in the peptide size distribution. So things have moved on. Maybe there's been a lot of advances in manufacturing process that have improved this, but we still have an awful lot of variation in what's out there. And so we come back to the same issues of setting standards. As much as anything, both for the clinical community, but also the patients, is like understanding, what is that PHF? Is that what's right for my baby? Or an EHF, and are they always the same? And what's the standard and quality requirements? So what would we need? Okay, first of all, and I feel like having worked a lot, to be honest, much more in the area of allergen analysis for PAL and things like that, I feel like there's some of the same questions. We need agreed definitions and test methods. Heard that one before? Actually, one of the things I think we need are definitions, and I found it very interesting. I went and looked up in the Oxford English Dictionary what the definition of hypoallergenic was. Relatively unlikely to cause an allergic reaction. That sounds awfully British. Should that be in a food challenge patient? Is that enough of a definition? Maybe we need something that's better, that everybody agrees to. And actually, I think that's also important and relates almost to the free-from and some of the exemptions that we had out of the Codex, which I don't think Marie-Claude was covering so much, but there are connections between this. Chemical composition. Well, what is the peptide size distribution and how should we be measuring it? And what about those residual IgE epitope sequences? How do we bring the new kid on the block, protein mass spectrometry, to link into there, to link to the immunoreactivity? We have the same thing in allergen analysis with precautionary allergen labeling. And for me, partially and extensively should have defined peptide size distributions to ensure consistency across manufacturers, but you need to link that to the test methodology. And the last thing, and everybody knows this, I hope, who's ever worked with me, patients have always been at the heart of what I do. And I think actually we need to have the patients there, but we should have multi-stakeholder input. The clinicians, I mean, if they aren't on board and they understand this, how on earth can they actually recommend the right thing for their patients? We need the manufacturers there, medical societies, regulators, and I hope there's room as well for people like me as the basic scientists to actually contribute to this whole debate so we can drive that forward. So, thank you for listening.
Thank you very much, Claire, for this excursion into the chemical and the, of course, standard part of what's to do with the hydrolyzed formula for babies. Yeah, very interesting. So